Thank you very much for the introduction, and I'd like to thank the organizers for the invitation. I'm very happy this is such a wonderful conference. I'm very happy to be here. Okay, and everything that I'm going to describe today about work is joint work with Vivian Kuperberg, who's in the audience too. Okay, so in this talk, I'm going to be concerned with the K-divisor function. So as a reminder, this is over the numbers, over the integer numbers. This is the number of way of writing n as a product of K factors. And as we all know, it shows up as the coefficients of the Divisor function that one gets when we consider the K power of the zeta function. And we're interested in problems that have to do with the sum of the divisor function. So the initial problem that one can consider is the sum of the Kn, and then up to x. And this is well known to be, well, I mean, we get the principal, a main term coming from a residue of the zeta function, and is given by x times a polynomial of b k minus 1 in log x, and then there is an error term. So if we want to understand this formula, we need to understand the error term, and so people have been studying this, and so there are results. It has to do with understanding the size of the error term. So if we consider the variance, this is asymptotically should be well, that formula, the variance of delta when we consider between x and 2x, asymptotically should be x to the 1 minus 1 over k. This was proven by Kramer for k equals 2, and then Tom for k greater or equal than 3 under the Riemann hypothesis. And we are going to be concerning two variations of this question. So one has to do with distribution of intervals. Actually, to be honest, we are going to be concerned with variations of these two problems that I'm going to present. But first, let me start presenting the problems that are the most popular. So one has to do with distribution in intervals. So we consider this sum, but now in some interval of length h. And so then again, the error term is going to be the difference of the error terms that I had before. And the variance attached to this has been studied by various people. So I just want to mention the results by Lester, by Butila, Coppola, Salerno, Ibik, Lester, and Yesha again for k equals 2. The result of Lester, as before, k greater or equal than 3. Also Bounds by Milinovic and Butterworth for k greater or equal than 3. And that's the Riemann hypothesis. I'm not really giving you the results because in the next slide I'm going to tell you what the principal term should be. But the thing I want to point out here has to do with the intervals for h. Okay, so the length of the interval that I'm considering. So what is hard is to get short intervals. So for example, the result of Lester is with h between x to the 1 minus 1 over k and x to 1, essentially. And what is difficult if we have h less than x to the 1 minus 1 over k. And okay, so in general, there is a very nice and general conjecture due to Keating, Rodgers, Roditty-Gershon and Rudnick. And from now on, I'm going to call them KR3 because I'm going to mention them often. So they had this very beautiful paper from 2018 when they formulated conjecture of what this variance should be. And yeah, as you can see, the interval is much bigger. So we are considering, I mean, okay, the range of h is bigger. That's what I wanted to say, but with h smaller. So if we consider h to be x to the delta, okay, and delta between 0 and 1 minus 1 over k, then the asymptotics of this variance should be some constant ak that we already seen this constant before in this week, coming from the arithmetic factor, and then multiplied by some polynomial function. So it's a piecewise polynomial function in delta. So in this exponent of x times h times log of x to the k square minus 1. Okay, so let me, so this, I want to focus, so a focus here will be on this pk delta. So this, like I said, is a piecewise polynomial function in this delta, has degree k square minus 1. So, and it can be written more precisely using some integral. Okay, so after some normalization, we are going to call it gamma kc, and this is given by some integral. Okay, so it's, we have the delta, so delta c is a delta distribution, okay, translated by c. So what we have, or maybe I should use, yeah. So what we have here is a detector of when the sum of these k variables is c, okay. And well, there is some factorial in front. Anyway, so it's a very complete, very nice symmetric integral. Now, I want to mention the other problem, and then I tell you a bit more about the context of how these conjectures came to be. So the other problem that people are interested in has to do with, again, the sum of the divisor function, but now over arithmetic progressions, okay? And again, if we look at the variance, it was studied by various people. So, and again, here the issue has to do with the x. So I'm not giving the results of the people, but you can see the range of the x. And so the conjecture, again by KR3, has again an x in a larger range. Okay, so so this is for, okay, so for q prime, but so q is the modulus, so we're looking at n congruent to a modulo q. And so with x between q and q to the k, as x goes to infinity, this variance should be given by some formula. So x over q, again, times my ak that I had before, then the gamma kc now evaluated in log x over log q, and then a k squared minus 1 power of log q. Okay, so this is not, that mysterious is coming from normalizing, in a sense, the gamma k. So the k squared minus 1 exponent is the degree of the gamma k. Okay, so how these conjectures came to be? Well, they came from looking at things over function fields. And so, so basically what we have, q and odd prime power, and we are going to consider elements in fqt, so polynomials. And then in that context, we still have the divisor function that we can write dk of f as a way of writing f as a product of k monic factors. And again, it comes from the coefficients of the k power of the zeta function. And yes, so that's what the object of study. And then the two problems that I described before, they can be modeled in this context. So for the short interval problem, or maybe before that, let me just remind everybody that when I take the norm of f in this context, I just mean q to the degree of f. So this is the number of elements in the quotient of fqt by f. And again, so if we look at what happens to distribution in short intervals, so one way to model this is to consider the sum of decay f over f monic, over f monic, such that f is very close to a. So you fix a polynomial a, monic of say degree n, okay, and we're going to consider all the f that are closer to a than q to the h. Okay, so remember that this distance is q to the degree. So basically, if f minus a has a small degree, so that means it's close to a in the sense that the first coefficients of f coincide with the first coefficients of a. So that's the intuition. Okay, so the results that they get, okay, they can compute the average of this n decay ah. Okay, so that's the short computation, and then they consider the variance. Okay, so if we consider the variance, then what KR3 do is that as q goes to infinity, then the variance can be described by this integral over unitary matrices. So what we have is the absolute value square of the sum of a product of secular coefficients over, okay, so what are the secular coefficients? They are the coefficients of essentially the characteristic polynomial with this normalization of the characteristic polynomial. So 1 plus xu, okay, so u my matrix. And then we take the products of the secular coefficients such that the index, the sum of the indexes is fixed to be n. Yeah, and then, yeah, so basically all the possibilities that with the sum of the indexes fixed. And so that's the result they get. And I'm not going to describe how this is proven, because I'm going to focus on similar results that we got, and then I'm going to describe those in more detail. But let me also talk about the other side, so the problem with arithmetic progressions. Then in that case, one can also compute the mean with a main term of the mean. And then again, there is a very similar result. And here, I put a star here because this variance is computed with this, the main term. I mean, not the mean completely, but the main term. But essentially, the integrand is essentially the same. Okay, we have, well, different parameters because we have a different problem, but essentially the point is that the integral is the same. And so this is where the gamma kc is going to come from. Okay, so the goal then is to understand this integral, and there are quite a few things that they do to understand. So one is to relate this number to a certain count of lattice points in the lattice C to the k square that lie inside a polytope. Okay, the gamma kc that we have in the formulas, this is coming from the asymptotic of the main term. So this I chi, this integral is given in principle is some polynomial of degree k squared minus 1 in n. Okay, so the main term is k squared n to the k squared minus 1 times something. And so the gamma kc that I was describing before is a coefficient of n to the k squared minus 1. Okay, and the normalization, so the C has to do with normalizing small n over big N. And so, like I said before, this gamma kc is a piecewise polynomial function. Okay, so it's given by this integral that I showed you before. And so here's an example. Actually, yeah, I didn't have more room to write maybe a more interesting example. So when k is larger, this is going to be more interesting. But here's an example with gamma 2c. So when you have k equals 3, you're going to have 3 pieces and so on. Okay, so this is just 2 pieces. Okay. So our project started with actually part of the FRG at AIM. So we had a group about like, let's talk about gamma kc and various versions of gamma kc. And so the question was, what about symplectic distributions? Okay, so what I just showed you is this integral over unitary matrices. So what if we try to get some similar situation with symplectic matrices? Okay, so how do we approach this? Okay, I didn't really tell you what KR3 did to prove the result. But the idea of why we had this distribution is essentially to compute this variance. You pick up terms using characters, okay, and then you play with that. You get a sum, and then you get the final result with the integral by applying some equidistribution theorem by Katz. And so to pick up the variance in the case where we have short intervals, they work with even primitive characters. To pick up the variance in arithmetic progressions, they work with all primitive characters. So then we said, okay, so we want to work with square-free. So we want to work on square-free quadratic extension. Sorry. So y squared equals something square-free. Okay, so we said quadratic character with conductor D moniker is square-free. Okay, so that was the first attempt. But then actually it's not so easy. Like, this is kind of going backwards, right? Reverse engineering, like, let's get an interesting problem that has the solution I want. And but it's not so easy to work with those actually, because it's, so this is the first problem that we consider. But actually, it's not so clear how to pick up squares if you have a whole conductor D. So then we said, I mean, not so easy in the sense that you have to do a lot of combinatorics, and then the sum you consider becomes really cumbersome to work with. So then we said, okay, let's make our life simpler and work with prime conductor. But of course, if we work with prime conductor, then we have to pay for it somewhere else. So this is going to come back. So then the problem we considered was the sum of the divisor function going over f is a square modulo p. So we fix monic irreducible polynomial of degree 2g plus 1. And we are going over f congruent to square mod p. And I'm going to call it S again. So this is not the same problem that I described before from KR3, but the point is that it's morally similar. So it's not really arithmetic progressions, it's a square mod P. Okay, but yeah, there's a reason I'm doing this, is because then I'm going to talk about another problem morally equivalent to short intervals. And so this is what we got. So we were able to, okay, not even the mean in this case, we can estimate, we estimate what this sum is for any prime, the estimate is independent of any prime p. So this gives a main term for the mean if we want, but also in general for each individual term. And then computing the variance using this main term. we get to a very similar integral. So again, the sum inside is the same we had before, okay? But now the integral takes place over the symplectic matrices, and we're taking, okay, so I wrote absolute value square, so there's no need to take the absolute value here, okay? It's just, it cannot need to write it with a similar notation. So I guess I have absolute value square everywhere, but I mean, this is not a complex number. And the square though is there because I mean, we want the variance. And that's also something that is going to come to haunt us later. Okay, so I want to mention some ingredients in the proof, okay? So one thing, let me just mention quickly about quadratic character. So say we work with Q congruent to 1 mod 4, so we don't have to worry about quadratic reciprocity. And then for P monic irreducible, we can define the quadratic character using the Legendre symbol. And then we can extend it modulo, say, D. Okay, so we define it for P prime, but then we can extend it modulo D by multiplicativity. And then, so then the character that I'm going to consider, well, technically is df. And I just want to mention one thing that is relevant. So when the degree of D, okay, so this D is a product of primes. So when actually, okay, so what I wrote here should be for D square free, sorry. But when the degree of D is odd, then the character is odd. So this, what it means is that it will give something non-trivial on the constants of FQ. So this is also something that is relevant, okay? Now, we can understand this also from the geometry. Okay, so if we have D square free, okay, and this is the D that I had before, we can consider, say, the hyperelliptic curve defined by the equation y squared equals dt. Then the base zeta function, we can consider the base zeta function, and then the L function attached to the character that I just described shows up as the numerator of the zeta function. And then the Weil conjectures imply that if we fix D, okay, so D now is a square free and has degree 2g plus 1. Then the L function is a polynomial of degree 2g. It satisfies a functional equation. And it satisfies the Riemann hypothesis, which in this context is says that the absolute all the zeros are at absolute value of u equals 1 over the square root of q. So the connection between this and s, the variable s, is given by taking the change of variables u equals q to the minus s. So we could write all of these in terms of S, and then we will have something in a language that is more similar to what we have our number fields. And one thing I wanted to mention, yeah, also is that this curve, okay, so it's a particular model for a curve, and it has genus G. So this 2G plus 1, the G is coming from the G. And the way I'm setting things so that the degree is odd, okay, has to do with having the character odd. And I could have things for even, but I will sort of, it will be just different models for the same object. So it's better to fix odd and just yeah, like choose a model. Yeah. Now, okay, so we take this our L function, okay? And the L function can be written, well, by the Riemann hypothesis, if you want. I mean, we can connect it to that. We can see it as actually the characteristic polynomial of so 1 minus uq to the 1/2. Okay, so this we see, and by the Riemann hypothesis, we have that all these normalized roots have to have absolute value 1. So, and yeah, they have to be real. So basically what we get is that what we can set here is a matrix, actually is a conjugacy class. It's called the Frobenius conjugacy class, and it lies in the symplectic group of dimension 2G. And then, okay, so far it's not clear how you get the divisor function, but actually the divisor function comes from taking the k power of this L function. So you take the k power and you end up with the divisor function twisted by the character. And so we can play with this, okay, essentially. And so developing this determinant, we can write this type of sum as a sum involving the secular coefficients. So this is the sum that we have inside the integral. Okay. Okay, so basically what this ends up giving is that this is, let me remind you, so this is the sum over f congruent to a square mod p. Okay. So it gives something with when we have a term coming from essentially the principal. So we have 1 plus phi p. So because we want to detect squares, so there's a term coming from the 1 that doesn't have the condition on the square anymore. So it's a nice sum that we can compute. And then we have a term coming from the character, so with the character twist. And so for this term, okay, so this is the main term. Okay. And this we can compute just by looking at the generating function. But this is a very simple computation. So the generating function of this sum, okay, is essentially the Riemann zeta function, the zeta function to the power of k, but you have to get rid of p dividing f. And then this other term is smaller, and we can bound it with the Riemann hypothesis. So it has about a size about q to the n over 2 versus the main term that has a size q to the n. Okay, so when we write the variance, like I said, we compute the variance by subtracting the main term, okay, the main term in the mean. So then we end up with this sum of absolute value m square. Okay, it doesn't have to be absolute value, just a square. And then when we replace, we get this term that we had in the statement, except that we have a sum and not the integral. Okay. So to get the integral, we need an distribution result. Okay, so the family we are considering. Okay, so the family we wanted to consider, let me say that, because this is the family that we wanted to consider originally, had to do with the square-free polynomials of degree 2g plus 1, and this is known to be equidistributed with the symplectic group. So this is what we wanted to consider. However, that's not what we have, because we said, okay, we don't want to work with this whole family, we want to work just with the primes. Okay, so basically we are working with y squared equals prime. Okay, and that we weren't sure about it. We couldn't find actually reference in the literature about what was the, whether there was an equidistribution result for that. So we actually went and asked Nick Katz, who was very nice and came up with help for us. Okay, so basically The idea is that we consider different factorization types. So instead of taking just the whole H, so the square-free polynomials of degree 2g plus 1, we fix certain factorization. So I'm going to call H d1 to dn to be the f in H dg plus 1, so the square-free polynomials of degree 2g plus 1, that necessarily can be written as a product of f di with f di monic and degree of f di equals di. What I mean by this is that I'm forcing f to have certain factorization, but f di doesn't have to be prime or anything. Okay, it could have more, it could be further factorizable. But the point is, well, say if I have more than one index here, I cannot have a prime, for example. I cannot have an irreducible polynomial. And so the idea is that there is, in fact, a result like that for fixing certain partition. Okay, so if we fix a partition, then there is a result like that. And yeah, I'm not really an expert on this. So let me just say more or less the idea, but I apologize if I say something wrong. So the idea is that the monodromy group of y squared equals f with f in this set is actually a subgroup of the symplectic group. And then it contains a monodromy of having a finer factorization, so x minus t times the rest. And so the rest, this f2g, will leave, say, I extract a factor of one of the first, I extract a linear factor of the first factor. And this is known to be sp2g. And so the idea is that it fits in a sandwich between something that is a whole group and something that is a whole group. Now, okay, so once we have that, then if we want the primes, okay, so we want the primes, so now we really want the factorization type, but that is relatively elementary compared to the other thing, some inclusion-exclusion argument. Okay, so with some inclusion-exclusion argument, then we can get a fixed factorization type where I fix exactly the degrees of the irreducible. Okay, and in particular, we get the result for prime. But this is a very beautiful result that applies to any factorization type. So it's I just wanted to mention it because it's really nice. Okay, so this is here finishes the ideas in the proof. Now what we want to do is we want to understand this integral better. Okay, so this is the integral that we want to understand better. So again, I remind people that we don't need the absolute value, but we do need the square. I put it in red. I mean, we need the square from the point of view, okay, we're coming from number theory and we care about this integral. So people coming from random matrix theory don't feel so excited about the square. And they are right. I mean, the square is really painful. Okay, so one thing we did was to study this using symmetric function theory. So this is also something that KR3 do. And okay, so let me just give some generalities here. So we're going to consider a partition lambda of n that has length r, say, is a sequence of lambda 1 greater or equal than lambda 2 greater or equal blah blah up to lambda r of positive integers such that the sum is n. A semi-standard Young tableau which says TIG is given. Okay, so okay, so the indexes of the cells. So it's a diagram with this. So each of these squares is a cell. The length of the rows are the lambdas. Okay. So in this case, I have lambda 1 equals 6, lambda 2 equals 4, lambda 3 equals 2, lambda 4 equals 2. And okay, so if I just write the cells, this is what is called a Ferrer diagram sometimes. But I'm interested in a Young tableau, so I'm going to fill these cells with numbers, so with positive numbers. And they have to satisfy that in each row, the sequence of numbers is non-decreasing, so it's less or equal, okay, 1, 1, 2, 3, 5, 5, so on. And then when I go down in each column, the sequence is strictly increasing. So that's what semi-standard means. Okay, I believe standard is that the sequence is strictly increasing in the rows too. And then a semi-standard Young tableau T has type A1, A2, and so on. So the AIs are going to count the number of cells that have value I. So for example, here we have A1 equals 2 because there are 2 ones, A2 equals 3, and so on. And then the sure function is given by, if I fix a partition lambda, okay, I'm going to take the sum over all the semi-standard Young tableau of shape lambda. So shape means the shape. Okay, so the lambda 1 is fixed, the lambda 2 fixed, and so on. Okay, whose entries belong to 1 up to R. So if I have x1, xr, so I have R variables, okay, I'm going to take the sum of t. I'm going to take x1 to the a1 of t. So a1 is the number of ones we have, and so on up to a xr to the r, which is the number of r's that we have. Okay, so that's the sure function. And then there is a result of Bump and Gamble that says that if we take the, okay, so we take the integral of the product of the characteristic polynomials on symplectic matrices of dimension 2n, okay, then that, okay, so that integral was, for example, has this formula that shows up in a paper of Conry, Farmer, Keating, Rubinstein, Snake. But it can also be written using sure functions. So the reason I described all the Young diagrams and everything before had to do with this. So, so we can understand this integral in terms of a sum over sure functions, and the sum takes place over all the partitions that have lambda 1 bounded by 2n, okay, and lambda even. And lambda even means that each of the lambda i's is even. So in particular, the example I wrote here is an even partition because each row has an even number of cells. Okay. Now, having this formula, we can use this formula to write a generating function for the integrals that we want, okay? And so the way we do it is, so the general formula is with, say, R variables, okay? So we fix the first, we take R equals to K, we fix the first K variable to be X, the second set of K variables to be Y. And so this is what we have. So we're going to have the sum of the sure function, but now evaluated like that. And if we write the coefficients of this generating function, well, the thing I'm interested in has to do with having m equals n. Okay, so the integral I want to find comes from setting m equals n here. And so this, again, so this n equals n, have to do with the square. Okay, so I'm keeping these two variables to keep the square there. Okay, so what we can do now is we can look in detail about what this gives in the sum of the Schur function. Okay, so having n and n is equivalent to forcing the sum of, okay, so the number of cells with the numbers up 1 to k to be the sum of all the, I mean, the total number of these cells to be n, and also the cells with number k plus 1 to 2k to be n. And so we can parameterize the Young tableau using an idea that actually is coming from KR3. So we take YRS to be the rightmost position of the entry S in the row R. And so this gives some matrix that is like upper triangular matrix with certain conditions. Okay, so this is quite technical, okay, but basically, so these parameters, they have to be in certain interval because the lambda 1 is at most 2n. There are certain inequalities that have to do with having a semi-standard Young tableau. The sum that is n and the sum that is 2n, they come from these conditions. So this is coming from wanting to have these diagonal terms x to the n, y to the n. And then there is the condition that the partition has to be even. So that gives a condition on the y's. And so the point is that we want to count all the solutions to this. Okay, all the possible solutions, all the possible y's that fit all these conditions. And so this can be done by, yeah, sorry, I put too many lines here. Let me just put it every together. So this can be done by, you scale, you normalize, and what you get is a certain polytope that is a convex polytope defined by inequalities, right? And to count the number of solutions y ends up being the same as counting the number of points in a certain lattice intersecting this polytope. And the lattice is a bit so technical, so some numbers have to be even. And so this is, so I wrote a little e here because some of the there are 2k minus 1 variables that have to be even. But the whole point is that essentially you count the degree of freedom you have. And when you count the degree of freedom, what you find out is that you get 2k squared plus k minus 2. And so, okay, you can do this much more formally than what I'm describing with my words, but what this ends up giving by Erhard's theory is that the integral that I want to find out is given for a fixed c, is given by a polynomial of degree 2k squared plus k minus 2 on n. Okay, so all this work, what this gave me is an intuition of what the degree should be. So the gamma kc from the original work of KR3 for unitary matrices has degree k squared minus 1. And what we are predicting here is that this gamma kc should have a degree 2k squared plus k minus 2. Now, well, we can go further. I mean, with the formula that I showed you before, I mean, there is a formula computing the integral, the one, sorry. Yeah, the formula that I have here. Okay, so in principle, we can compute this. And to compute it actually is good to write it in terms of determinants. And so this is an idea, and many of these ideas actually came from discussions, like I said, in a group, in an N group, work talking about gamma kc, and in particular work of Matilde and Rubinstein, where they came up with using a formula is called the Armenian Stenbridge-Proctor formula. They can write, one can write, I mean, this is in the literature actually. So one can write the sum over two functions now as a determinant. And so what this means, okay, so this is for several variables. Now, if we want to fix x and y, we end up with lots of singularities. So it's like a L'Hopital rule that we have to apply everywhere. And so that's the idea that Matilde and Rubinstein use. And so we adapted to our case. And what this gives is that this very ugly determinant, okay, that it should remind you of problem 1 in the problem session yesterday. So this is kind of coming from the same place. And I want to bring attention to a couple of things here. So one is, there is a term here, y minus x to the k squared. That term comes from the fact that we are still keeping two variables because we have a square in the integral. And it's a lot of pain because everything else you can develop as a Taylor series. And I mean, it should give a polynomial, but at least you have a Taylor series, you can keep track of the coefficients, but dividing by y minus x to the k squared is kind of, yeah, it looks fishy, but actually it's not. One can actually prove that this term divides the determinant. So this all works well, but yeah, it's complicated. And obviously computing the determinant is complicated, but one thing that we can do is to compute what we call the zero subterms. Okay, so we ignore the capital N. So when we take terms that are small enough, okay, so these terms have capital N here. When we take terms that are small enough, we can compute the determinant here. And so this gives a formula for the integral in the very particular case that small n is less or equal than capital N. Okay, so this formula actually one can evaluate. So for k equals 1, it gives the integral of, yeah, it's a Fourier coefficient square. So this is very simple. And for people who are very familiar with this work, don't panic with the boundaries here. So I have 1/2, but this has to do with the normalization. I say don't panic because in the original paper, the whole point is that these transition points are integers. But this is because I divided by 2 capital N in my normalization. And yeah, for fun, we did k equals 2. Yeah, just to get an idea of how ugly it is. But this is not the whole story because this is only the zero subterm. So we are missing something here. Okay, so this formula is between 0 and 1/2 and 3/2 and 2. There is some symmetry there that we can exploit, but we're missing what's happening in the middle. So this is still in progress. Okay, so this is just to remind you, this is a result that we got. And then with that and knowing the degree, we can make a conjecture about what to expect in the number field case. So in the number field case, we would be interested in the sum over the numbers less or equal than x that are congruent to n mod p, p doesn't divide n, dkn. And so what we speculate is that if we consider the variance of this, okay, taking for p between y and 2y, say, it should be given by a formula like that. So it's a k, so it's an arithmetic term now coming from the symplectic distribution. So given by this formula. And there's the gamma kc that I had before, okay? And now the degree is 2k squared plus k minus 2. So this is what we can conjecture with knowing this. Okay. Okay, so here I have the formula for the variance to be clear because yeah, sometimes it gets quite confusing what this is. Okay, so I wanted to mention something else. So there is so far what I discussed had to do with this problem that is square modulo P. Okay, so it's like I said, it's kind of analog to arithmetic progressions. But the other problem that I started talking about at the beginning had to do with short intervals. So I'm not going to give details on this, but there is a setting that, that is quite analogous to short intervals, and it has to do with looking at, okay, so the original problem has to do with looking at distribution of arguments of Gaussian primes. And this was a problem that was considered by Rudnick and Waxman. And what they did is they modeled this with function fields as well. And so the problem over function fields will be, again, the sum of the divisor function, f monic of fixed degree. Okay, so f of 0 different from 0. This is some technical condition we need. And then something that is akin to the argument has to lie in certain sector of the unit circle. Okay, so my sector of the unit circle is going to be defined as depending on A. So A will be the middle point, as I had before, the middle point for an interval, and then the width, H will be the width. Okay, and I didn't say what S1 is. Okay, so the idea, like I said, this is coming from modeling the Gaussian primes. So the idea is that we take a square root of t. Okay, so we're working on FQ of t. We take a square root of t. Okay, so that would be my I. Okay, and so then we're working with power series, in fact, on this square root of t. And so in that context, we can look at things that have absolute value 1. Okay, so this would be the norm, right? It's the series times the conjugate. Okay, the way I have it written, yeah, it's not a series, but okay, there's a more general context. And then one can define the argument in the way that you would define. Okay, so you divide the element by the conjugate and you take the square root. And this is something that can be done. I mean, I'm not giving any details. And this is related to, so in the number field setting, this will be related to moments of Hecke-L functions. Okay, so and so there is work by Duke, Freelander, and Vanek on this. And you can see the word that is the symplectic distribution there. So what we prove is a very similar statement. So by now all these integrals, they all look the same. Okay, so it's the same sum, but now integrating again over the symplectic matrices. The eta here is, okay, so H is the width of, actually twice the 2H is the width of the sector. So we have a result like that, and the reason I wanted to mention this, okay, so first of all, because it's related to the short interval question, but also because there is an orthogonal setting related to this. So the way Rudnick and Waxman model their question, and they look at distribution of primes, so they work with the von Mangold function. So we replace that by the divisor function. And basically, the way this is modeled, so is by using super even characters. Okay, so I'm not going to describe that, but basically certain family of even characters. And there is a result of Katz in a paper that is called On a Question of Rudnick and Waxman, where he proves that these super even characters are become uniformly distributed on the symplectic loop. And then And then in this paper, the same paper, Katz considers a twisting of this family. So if we take chi2 of f to be just chi2 of f0, where it gives 1 if f of 0 is a square and minus 1 if not. So if f of 0 is different from 0. Then this is x squares, and then the result is that if we consider the twisting, so not the super event vector, but the twisting by chi2, then this becomes uniformly distributed over the orthogonal matrices. And so we're interested in this, so to explore the orthogonal side, the orthogonal family side. So in principle, we could get we can modify our question, our problem, okay, to lead to an orthogonal distribution. And this is not very difficult to do from what we were doing before. Okay, so this will be the same problem, so a similar problem. So the f that lie in certain sector of the unit circle, but now we are also asking a condition on f0. So this is going to detect when f0 is a square. Okay. So we have that, and so as sort of current and future plans, short and long term, we want to have a better understanding of this gamma kc in the symplectic case. So some things that are missing from this picture have to do the matrix integral. So there's this integral that I gave you at the very beginning of gamma kc using this delta distribution. We don't have anything nice like that. It looks like we cannot get it, but okay, maybe discussion in progress. So that's the delta integral, and then the matrix integral. So it's a way of understanding this directly from the random matrix integral, and that we also still don't have because of this nasty term that we have x minus y dividing. And obviously, it would be interesting to get lower terms. Okay, so the gamma kc is just the asymptotic of n to the highest power, but we could go to lower powers. Obviously, with the orthogonal case, we have questions about all of the above, okay, and also the degree. So we're working now on the symmetric function theory for that, and it's a bit more complicated than the symplectic case. All of the above for von Mangold convolutions, so we've done some work on them. So many of the things translate, but we still need to have a better understanding of the gamma case of those. And yes, and then for more longer terms, one could ask questions about other L functions like higher degree. Okay, so R is in degree 1. Okay, and with that, I'd like to thank you very much.
Thank you very much. Right, are there any questions? Yes.
So, I mean, you said you were interested in lower order terms of these integrals, but already with the results of CATS, this is only kind of giving you a main term. Is anything known about like the error in those results?
So what I mean by lower terms, I mean this we can compute in principle. I mean, we have n to the, say in the unitary case, n to the k square minus 1, but then we have n to the k square minus 2. And so it's the coefficient of that, say.
This is after taking the logical limit.
Yeah, yes, after taking the limit.
Andy's thesis of the unitary case has a discussion about the lower terms that he was able to get from his determinantal expression. So.
Yeah, exactly. So yeah, I should have said that. So for the unitary case, the determinant expression is much better. And so from there, yeah, Andy has all this discussion. But the symplectic case, and especially, okay, maybe it's a bit of, I don't know. It's just because we insist on having this square. I mean, part of the difficulty is having the square in the integral. I mean, of course, we could decide that let's forget about the number theory, just focus on this integral, and then life will be easier. I have to admit.
Are there other questions? Thanks again, Matilda.
Okay.